Bismillah ar-Rahman ar-Rahim. We have a sequence of zero mean i.i.d random variables. Each one has a finite variance of sigma squared. We have another sequence of random variables, M₁, M₂, M₃, and so on. These random variables are independent of each other. They are also independent of the x random variables. These random variables are discrete. Specifically, Mn is a Poisson random variable with parameter theta n squared, where theta is a positive real number. Recall that if z is Poisson with parameter lambda, the probability that random variable z is equal to k is lambda to the k e to the minus lambda over k factorial. K is a non-negative integer. We are interested in the convergence in distribution of yn as n tends to infinity, where yn is defined as the sum from x1 to xmn. This sum is divided by 7n plus the square root of n. The characteristic function of the random variable yn is the expectation of e to the I u yn, where u is real valued. This is the expectation of e to the I u over 7n plus the square root of n, the sum from x1 to xmn. We use the law of iterated expectations. This expectation can be written as an outer expectation with respect to mn. We have an inner expectation that is conditioned on mn. The x random variables are i.i.d, so the inner expectation is the characteristic function of the random variable x1 evaluated at u over 7n plus the square root of n. This characteristic function is raised to the power mn. The characteristic function of yn is the expectation of the characteristic function of x1 evaluated at this value and raised to the power mn. Mn is Poisson with parameter theta n squared. This expectation is equal to summation over non-negative integer k of the probability that mn is equal to k times phi of x1 raised to the power k. This is equal to summation k from 0 to infinity theta n squared to the power k e to the minus theta n squared divided by k factorial. Then we have the characteristic function of x1 raised to the power k. We can take this term outside the sum. We have summation k from 0 to infinity. Downstairs we have the factorial of k. Upstairs we have a quantity to the power k, which is theta n squared, the characteristic function of x1. This sum is e to the power this quantity here. We also have this exponential. This is the characteristic function of yn. The natural logarithm of the characteristic function of yn is equal to theta n squared between brackets the characteristic function of x1 evaluated at u over 7n plus the square root of n minus 1. To investigate the distribution of yn as n tends to infinity, we investigate the limit of the log characteristic function as n tends to infinity. Let alpha be equal to 1 over 7n plus the square root of n. Multiply and divide by alpha squared. So we have theta n squared alpha squared phi x1 of alpha u minus 1 divided by alpha squared. We need now to compute two limits. Limit as n tends to infinity n squared alpha squared, which is the limit as n tends to infinity of n squared over 7n plus square root n whole squared. This is 1 over 49. We also need to investigate the limit as alpha tends to 0 of phi x1 of alpha u minus 1 over alpha squared. The characteristic function of random variable z is expectation of e to the I u z. The characteristic function evaluated at 0 is equal to 1. So if alpha is equal to 0, then numerator is 1 minus 1, which is 0. The denominator is also equal to 0. Let's apply L'Hopital's rule. This limit is equal to the limit as alpha tends to 0 of the ratio of the first derivatives. Recall that random variable x1 has a finite variance, so phi of x1 is twice differentiable. We are justified in differentiating this characteristic function with respect to alpha. If the characteristic function is differentiable v times, then the vth derivative of the characteristic function evaluated at 0 is equal to I to the power v times the expectation of z to the power v. When v is equal to 1, the first derivative of the characteristic function evaluated at 0 is I times the first moment. Random variable x1 is 0 mean, so if alpha is 0, we have 0 in the numerator. We also have 0 in the denominator. We need to apply L'Hopital's rule again. We are justified in doing so because the characteristic function of the x random variables is twice differentiable. The derivative of 2 alpha is 2. The derivative of the first derivative is the second derivative. By the chain rule, we have another u, so here we get u squared. If we set alpha equal to 0, we don't have 0 in the denominator. In the numerator, we have the second derivative evaluated at 0 multiplied by I squared. So this is equal to minus the second moment of the variance of x1, which is sigma squared. We also have u squared over 2. the limit as n tends to infinity of the log characteristic function of the random variable yn is equal to theta times 1 over 49 times minus sigma squared u squared over 2. This is equal to minus 1/2 u squared theta sigma squared over 49. The limit as n tends to infinity of the characteristic function is equal to e to the minus 1/2 u squared theta sigma squared over 49. The limit here is a continuous function at u equals 0. So by Levi's continuity theorem, we do have convergence in distribution to the distribution of the random variable with this characteristic function. This characteristic function is that of a zero mean Gaussian random variable with variance theta sigma squared over 49. The random variable yn, which is equal to 1 over 7n plus square root n, the sum from x1 to xmn, where mn is Poisson, with parameter theta n squared, converges in distribution to a zero mean Gaussian random variable with variance equal to theta sigma squared over 49.